first I want to give you a bigger picture of this project so that you understand what this is all about. We have developed a software called Megamol, which is a molecular dynamics visualization tool. It's written in C++, a desktop application, and it has a lot of different visualization and visual analysis tools for this kind of simulations. And what we are currently planning to do is to build a web front end for this visualization tool, so that it can be used as a web service, and so that and then we are planning to incorporate collaborative tools and take data, look at data together, and connect researchers from all over the globe. So. But of course, as I said, this is a desktop software, so we are using state-of-the-art rendering and visualization modalities here, and we want to bring these to our web service, to our web service. Of course, there are a lot of molecular visualization tools out there. Some of them are quite established. For example, JMOL, which is, for example, used by the Protein Data Bank, the standard web storage, so to say, for protein data. Then there's JSMol for JavaScript for JMol, but also other tools like Chemdoodle web components that use very new technologies. And but most of these tools, frankly, are still Java or JavaScript. Some of them are using WebGL, like JSMol now, and HTML5, some more Flash, and so on. So kinds of technologies are used. But we want to focus on JavaScript and WebGL, so that the user doesn't have to install any plugins to his or her browser, and wants to have, well, of course, we needed to have the native hardware support, GPU support that WebGL offers. And but of course, there are limitations. So we are basically limited to OpenGL ES 2.0, which is same as WebGL, to make this web service available also on mobile devices. So, as I said, we want to have the current state-of-the-art in molecular visualization that is used in desktop workstations. And one of the most often used and most basic models is the space filling models for molecular visualization. You can see this here. We have all atoms represented by spheres. And traditionally, objects like spheres are rendered by tessellating them, using final-based representations, and we all know the problems here. So you get something like this, where you have a very coarse tessellation that renders fast, or you have something like that, which is very smooth, and but it renders quite slow if you have a lot of spheres, because you have too many dimensions. And even with instancing, this can cause problems. So nowadays, on desktop machines, you use GPU raycasting for something like that. But the idea is pretty simple. It's like ray tracing with only primary rays, so no shadow rays in the past. And all spheres can be rendered individually. So for each sphere, you draw a little rectangle on your screen that covers the whole sphere, and for each fragment that's covered, you cast a ray, and you do the ray sphere intersection and shade your pixel if the sphere is hit. And if you have intersecting spheres, like you normally have in a molecule, you have to write the correct fragment depth to get the correct fragment regardless of the sorting of the spheres. And this is, gives, of course, a pixel-perfect representation for our spheres regardless of the zoom level. And it's even faster than rendering trials on modern GPUs. But if you want to implement this in WebGL, we of course have the problem that in standard WebGL we can't write the fragment depth. Right now there is this new extract depth extension, but this is, as far as I know, only available since June this year, and so it wasn't available when we started this project. And I guess on OpenGL ES2 hardware, also on mobile devices, is not available at all. So we need to work on this fragment depth problem. The basic idea, as I said, is ray tracing, so we can just intersect all our spheres, with our ray. But this is too expensive if we test each ray with all spheres in our scheme. So we need a spatial acceleration structure, as it's commonly used in real-time ray tracing. And here we decided to use a uniform 3D grid because it's simply a GPU or GLI-style-friendly data structure, so it can be accessed very rapidly during rendering in the machine. And this idea was also recently used on desktop machines to render very large numbers of instances of the same protein. So here you can see a whole cell simulation which has 25 billion of atoms. So how do you pass this raycasting work? First, we needed to pre-process our data, so all our atoms are sorted into this acceleration grid. You can see the sketch here. So you have our atoms are embedded into a bounding box, which is acceleration grid. And we do box-box intersection tests to intersect the bounding box of individual atoms with our grid cells and sort each atom into all grid cells that cover this atom. And again, we need a workaround for 3D textures. So if we upload this grid to the GPU, we can't use a 3D texture like we would do on a regular desktop machine. We have to renderize our 3D texture and store it in 2D texture. And the same is true for the atom positions and radii and colors. So we have data structures to store all this information. And all this setup has to be done only once for a static data set. So all this pre-processing is executed once. Here you can see the data structures again. We have the acceleration grid with our atoms. So for example, the green atom is in these two grid cells. So in our table of grid cells, it's sorted into these two grid cells. Then the X and Y components point to a slot in the index and the number of atoms which are in this cell. And then we here, the indices point to the actual position and color data for our spheres. So this is very easy to traverse in the random shape. During rendering, we first render like in volume rendering, which some of you might be familiar. We just render the front side of our bounding box, and then we can start our arrays for each pixel that's covered by the bounding box. We can compute the length, and then we just traverse our separation grid. So here are our results. These first two grid cells are empty. In the next grid cell, we find some atoms, but our array doesn't fit any atom, and here in the fourth grid cell, some atoms are hit, so we find the closest hit point on our array, and then we can either do an array translation once the first hit point is found, or we can traverse the array until the end of the bounding box. For example, if you want to have things like transparency or something else. This was the basic rendering algorithm, and we have two implementations for the data processing. So one is the client side, and another is the server side processing. You can see a flowchart here. So first, the user selects ID from the protein data bank, the protein he or she wants to see, and then the server side application loads the data. And the client-side pre-processing, all this data, this protein data, basically atom coordinates, are sent back to the client. And here, all the acceleration grid structures, textures are built and sent to the GPU for rendering. Now, on the server-side pre-processing, the data structures are built in the server, and all this data is sent back to the client. The problem with server-side pre-processing, of course, is that we have to send much more data to the client. But on the other hand, the client-side pre-processing is in JavaScript, which is not that fast. So our application is currently a Java implementation. And if you now look at the performance results, we can see that preprocessing on the server is much faster than in JavaScript. So even though the data which has to be sent back to the client is much larger, the rendering is faster, or even the preprocessing is faster on the server. Please note that data sizes are very large because we're currently using a text-based format. I'll mention this in future, but we of course want to use binary formats in the future. But as I said, even with this text-based format, which produces a very large amount of data, server-side preprocessing and data loading is still faster than using client-side preprocessing. Rendering speeds, of course, the same for both implementations, since the data has to be uploaded once for static data. So for a protein of close to 100,000 atoms, we still get 30 frames per second, which is quite impressive. And I mentioned this is on a kind of not so new mid-range gaming machine. So you need, of course, decent hardware, but not really fancy. Visual quality, as I said, you get pixel perfect rendering of your spheres, and I hope that I have time to show a demo on the top. So we're very satisfied with the quality. It's the same as on desktop computer, and what we also implemented is volume rendering. As I said, this ray marching idea to do the ray casting is very similar to volume rendering, where you also have a grid, so to say, that the ray goes through. And I won't go into detail here because this was also our implementation here is very similar to what we all presented here 2 years ago. And I just want to remind you they had the same problems here. So no 3D textures, so you need a texture atlas of stacked 2D slices of the volume. You have no 3D interpolation in hardware, so you have to do this manually. But still rendering interactively. We implemented this volume rendering, transfer function, so the user can set transfer function, and the volume rendering can also be blended with polygons and ray casting, so you have the opaque representation of your molecule. You can also combine volume rendering and other methods. Data preparation for the volume generation is also done on the server. As you maybe see here, we want to have a representation of the density of the atoms. So for each atom, use Gaussian density kernel, a distance-based density function. All these density functions are summed up in the whole volume. And then we get this density out, and by choosing the correct transfer function, we can either get something like that, which is a representation of the electron density, or something like this over here, which is more like the molecular surface. And the preprocessing here, as I said, is done on the server, because we're using CUDA for that. And in the current implementation volume data set, this is stored to permanent memory and loaded once the virtualization is requested. So for future work, as I said, we wanted to add a collaborative web-based front end for our Biomolecules tool. We're not there yet, but we're working on it. So for dynamic data, we would of course have to have a binary format for data transfer. So we're planning to use WebSockets here, fast data transfer to update data interactively. We also have to extend the server application. Right now, as I said, it's a JavaScript server. It's a proof of concept, so we want to use our MegaMol application to send, to compute molecular models in real time and send them back to the client for rendering. And of course, we want to add more ray intersection tests to our WebGL to be able to render also cylinders to get this stick model or molecular surfaces like this here, where you also need torus intersection tests. And now that this fragment depth extension is available on some devices and in some browsers, we also want to use this wherever possible, of course, because it should give better performance than our raycasting. But still, for devices like tablet PCs that only support WebGL 2, this way of launching is still necessary. So to sum up, we have shown an implementation of GPU raycasting for WebGL, which gives high image quality, which is the same as on the desktop machine, and it's faster than triangle rendering. We prefer the server-side preprocessing that I showed because it is faster and more flexible. So in the server we can use, for example, CUDA or other acceleration techniques which might not be available on the client. And of course, the server-based implementation will allow to reuse data for collaborative views. And so if we have preprocessed the data set, we can send out the preprocessed data to a lot of different clients. So that's all. Thank you for the attention, and I'll be happy to take questions. I think we have time for still the workshop.
No videos.
Here you can see a small protein. This is not running very good on my machine here because usually the Intel drivers I had to select some don't use this bug fix flags in Chrome here, but it still works as you can see. So So as you can see here, we zoom in, our spheres are still perfectly round, and we still get interactive frame rates. And with our prototype, we can select different coloring schemes for the data. And we can also right now, the demo is all on my computer. I have to mention that I didn't want to rely on the internet connection here. So here, client and server application running on my machine. So as I said here on this, something's happening here on this info office. It's not that fast here, but it still renders correctly. With JSMO, we were not able to load this model of about 60,000 atoms at all. So I don't know what happened there. I think the WebGL implementation of JSMO is still under development. But here we managed to load this. So thank you.
Thanks very much for the demo. Questions?
This is very nice, especially because it's ray tracing, right? One of the great things you can do with ray tracing are very impressive and accurate shadows and transparency. You mentioned transparency, I think, very briefly. Is that implemented, or is that coming, or how does that work with what you've already got?
It's not really implemented yet. It works. So we have made tests where we traverse the ring until the end of the molecule. So we execute all the intersection tests, and it's about I think 20% slower. So it's not. It doesn't have that much of an impact actually. And then we can just use additive blending if we place the ring until the end of the molecule.
And a follow-up question. When you have, in particular, molecular models based on spheres instead of a molecular surface or a volumetric rendering, which you also mentioned, but especially with spheres, if you use ambient occlusion, it provides a very pop. The molecule looks fantastic and just something you can reach out and quickly grab. Is that possible to implement with the radiocasting that you're doing?
Yes, it's actually quite easy. I would say there are two ways to do this. So for one thing, you can just cast secondary rays using this method, and you already have the acceleration grid to do this. So you can get kind of perfect ambient occlusion. But let me maybe quickly go back to the slide where I showed this. So we have also developed fast ambient occlusion method, which just uses something like the acceleration grid here. So what you can see here is the virus structure with transverse occlusion. And so here this uses something like this acceleration structure. So what we do here is just make text look up into the direction of the normal, into the acceleration grid, and if the grid cell that we are hit has a certain amount of atoms in it, we have an occlusion factor that is, depending on the number of atoms which are in this grid cell.
Is that an option you can turn on and off in the software?
It is in the desktop software,
Yeah.
but we haven't implemented it yet in WebGL. But we're of course planning to do this, so all the preliminary implementation is ready.
Thank you.